In fact, this is what researchers aimed for when they faced these NP problems. By the way, computational problem is called P-problem if there is a reasonably fast algorithm solving it. In other words, that algorithm computes the correct solution easily for any given problem instance. Thanks to the advancement of algorithmic techniques, we could get reasonably fast algorithms for many computational problems. That is, we could show that those problems are P-problems. On the other hand, there were some problems for which we could not think of any efficient algorithm, though they do not seem so difficult. NP problems are typical examples of such problems. During the 60s, programmers and researchers struggled with each NP problem that they encountered. Note that people did not know the notion of NP before Cook or Levin. Some clever people might have noticed this property in his own problem. Then, because of it, some of them expected that there should be a clever way to solve the problem efficiently. Cook, similarly Levin, gave a clear definition like this for this property. And what was more important is their discovery of a method to compare the hardness of computational problems. With this method, Cook, for example, mathematically proved that the satisfiability problem is the hardest problem, in some sense, among all NP problems. Richard Kopp, who was one of the audience when Cook presented his discovery, realized the importance of Cook's method and applied the method to several NP problems around him. These results had researchers realize the importance of the notion of NP and the hardness comparison among NP problems. Then it was shown that quite a good number of problems that people had struggled with, in fact, had the same hardness. In a nutshell, it was shown that they all are easy, that is P problems, or they all are computationally hard, or there is essentially no better way than checking all candidate solutions to solve these problems. Many problems that researchers had attacked individually were shown to be equivalent with respect to their computational hardness. Based on such investigations, people started believing that such NP problems are indeed very hard to solve in general, and they are not practically computable. This is called the P not equal NP conjecture. Since the discovery of Cook and Levin, the conjecture has been open. And it is regarded as one of the 7 millennium open problems in mathematics. By the way, there were some NP problems for which we could not show the highest computational hardness. In fact, for some of them, some very clever and efficient algorithms have been discovered more recently. Thus, among NP problems, some of them are P problems, that is, practically solvable problems, but the P not equal NP conjecture claims that within NP problems, there must be some problems that wouldn't be easily resolved as P problems. Since the discovery of Cook and Levin, the P not equal NP conjecture has been investigated in depth. And this research area, which is called computational complexity theory, is one of the main fields of research of computation. Well, you may wonder why we need to prove such a thing. How would discovering that NP problems like these are hard to solve make us happy? I do think there are 3 significant reasons to study this. First, people want to solve these problems. They are problems that came up in all aspects of our lives. For example, good scheduling is quite important in many situations in our society. Likewise, each of these problems has an important applications, and we want to solve them anyway. Of course, if P is not equal to NP, then we cannot hope for a perfect algorithm for them. Even so, our desire is to solve something or anything, whether they be individual or partial. Therefore, studying the difficulty itself like this helps us understand what aspects can be conquered and what types of partial problems could be more easily solved. It is for this reason that it becomes important to know where the difficulties lay and what is causing it to be practically unsolvable. The second one is more direct reason. In fact, the hardness of some NP problems is the basis of the public key cryptography. Let us recall the computational task of cryptanalysis. It is obtain a plain text M from a given ciphertext C only. In the public key cryptography, this task is indeed an NP problem. To see this, consider that you are given a candidate solution M prime, that is a candidate of the plain text for the ciphertext C. You can check its correctness by applying encryption to this M prime with the encryption key P. Checking it produces the ciphertext that you want to decrypt. Recall that this key P is a public key that is known by everyone. So everyone can check whether M prime is correct or not easily. So this is the property of NP problems. Thus, the computational task of cryptanalysis is indeed an NP problem. So the hardness of this NP problem is important. Do you remember? When we discussed the security of cryptography, I explained that the security is guaranteed computationally. This is in fact the computational hardness of this NP problem. So in this case, we really want that the problem is not solvable even partially. As I have mentioned a moment ago, there are those who wish to solve problems even if it were partially. But what I'm saying here is that there are times it is better to not have that resolved even partially. Actually, this is why we need to understand the hardness of NP problems more. By the result of Cook and Levin, we roughly know that all top NP problems are equally hard. But if we consider more carefully, there should be some difference among the hardness, and this difference could be significant for our daily life. The third motivation is for understanding the nature of computation. Investigating the P not equal NP conjecture is to study the limits of algorithmic efficiency. It is similar to the time when mathematicians studied the computability, the limits of computation, which led the emergence of computers. In the history of mathematics, a breakthrough idea has been discovered or a new theory has been established from time to time through the research of impossibility. Similar achievements have been established from the research of the limits of algorithmic efficiency. Let us see the trajectories since the discovery of Cook and Levin. As I mentioned, the hardness of NP problems are quite related to cryptography. In fact, the notion of public key cryptography and its basis have been established in computational complexity theory, which became the basis of cybersecurity. Then, computational learning, again another topic related to NP problems, has been proposed, which became the basis of various learning algorithms and the field called machine learning. In 1990s, the randomness in computation has been studied extensively again in computational complexity theory, which provided some key technologies in statistical algorithms used in big data analysis, which is now used a lot in data mining. In summary, our desire for resolving the P not equal NP conjecture has been a driving force for the development of the current ICT society. Note that conjecture is still open. And actually, we don't have any clue for resolving this conjecture. In other words, there are still many mysterious things about the nature of computation. So if you like, please jump into this attractive field.